This is Britt Caswell with another example video. In today's video, I'm covering example 3 from section 6-2 in the SavvasRealize Algebra 2 textbook. The goal of today's video is to understand continuously compounding interest. Alright, so if you watched our last video, you would remember that when you compound, so when you calculate interest, the more often that you do that calculation, the more interest is added, right? Because you're taking interest on interest. Okay, so example 3 here has a whole lot of yada yada. I'm just going to use their table that they use for the try it to explain it, but I'm also going to explain some of this stuff. So when we do calculations, right, like you guys probably would have seen in my last video, right? You do a calculation where your x is your number of times compounded. So first you'll have an amount here, then you compound again, it's a little higher. You compound again, it's a little higher, and again, and again, and again, right? So every time I compound, it gets me a point on this graph. So kind of what our goal here is to actually figure out, like, how can we turn this from being a dotted line to being a smooth line? How can we make it continuous? So in order to make the line continuous, we are going to use what's called the continuously compounded interest formula. Okay? What this does is this actually figures out the maximum amount of interest through each time value here. Okay? So to use this formula, you need to understand a little bit to it. Is this number called E? Alright, there is a mathematician. His name is Euler. Okay, not Euler, but Euler. I don't really like Euler because he named everything that he discovered after himself. However, he has a lot that he discovered within mathematics, so he's probably one of the greatest mathematicians ever. But I judge him for naming everything after himself. So we have this number E, which is Euler's number, and it's a constant. It's like pi. Okay, it goes on for forever without repeating, and it's about 2.7. Okay, every calculator has a button if it's scientific or higher that has an E button. A lot of people just call it the natural base, or they just call it E, something like that. And so this constant occurs when you do these different calculations where we change the number of time periods that we calculate something. So what Euler did was he noticed that as he calculated with bigger and bigger numbers for the number of time periods that were compounded, the value was approaching this number here. All right, now understand he did some magical hoodoo to get that number that goes on for forever. I don't really care what that magical hoodoo is, but the main point of this example is to introduce this formula, which you should probably write down on your formula page, and for you to understand that this is what these numbers are approaching to. So in the triad it says if I continued the table to 1 million, would the value in the count increase or decrease? Well, it's increasing, and you know because each time we go up by a power of 10, it's increasing. Okay, so mostly from this example, I don't necessarily think that Savvas really cares that you know how they got Euler's number, but just understand that we can look at a continuous compounding to fill in the dots here. Okay, fill in the blanks. Okay, so there we have it, guys. That's example 3. Example 4 looks at how to actually use this formula. Until next time.